We're in section 5.5, and we're going to talk about indirect proof. And the other way that you'll hear this referred to, and I would say probably the more common way, is proof by contradiction. Is a little more common for this type of thing. So what I want to do is start with a little bit of compare and contrast. So far what we've been doing in geometry is what we call direct reasoning. And we started, this is what we started doing in chapter 2 when we talked about the if and the then and the converse and the truth value and all of that kind of thing. That had to do with direct reasoning. For direct reasoning, what we do is we start with known facts. And sometimes in geometry, we'll start with a postulate. And the thing with postulates is we assume that they're true. So we know that they're true. We start with known facts, and then we connect other facts using logic. So that's what we've been doing so far. We know that this is true. Well, if this thing is true, then the next thing has to be true. Well, the next thing is true, then the next thing has to be true, and eventually we can put together enough known facts that we get to what we want to find out. So that's direct reasoning. Indirect reasoning. Indirect reasoning is a little different. Indirect reasoning, we consider a possibility. And I'm going to say possibilities because we can do it more than once. And then we prove them wrong until only one possibility is left. So an example of this is if you've ever done like a Sudoku in the newspaper. You start by saying, okay, I'm going to try putting a 4 in this space. Well, if the 4 goes in this space, then a 3 has to go in this space, and a 2 has to go in this space. Oh, that doesn't work because of the 2 that's already in this column. So 4 can't work. So you considered a possibility, and then you showed that it was wrong. You said, well, okay, then it must be 3. If 3 goes in here, then 4 must go here, and then 1 has to go here. Oh, no, the 1 messes up this row. So that one's wrong. And you do that until there's only one possibility left. That's an example of indirect reasoning. So what we're going to do today is talk about how we do an indirect proof. So to do an indirect proof, we need to do several things. The first thing that we do is assume temporarily that what we're trying to prove is wrong. So we want to prove temporarily the opposite of what we want to prove. So temporarily we assume the opposite. Just like with the Sudoku. We're not sure what we do, so we make an assumption. It's 4. And then we prove that so then we go on from there. We show then, our second step is show that this leads to a contradiction. And contradiction means something impossible or something wrong, something false. Well, if that's the case, then our temporary assumption must be wrong. So if we assume that something is true, and it leads to something impossible, if we assume that a 4 goes in this square, and that tells us that 1 has to go in this other square, and that's impossible, well then a 4 can't go in that square. That has to be wrong. And in the way that we're going to do an indirect proof, that means the original thing must be true. So the thing that we're trying to prove must be true. If the opposite of it leads to something impossible, then the original has to be true. And proof by contradiction, or an indirect proof, when you do a direct proof, you kind of, for me anyway, you feel smart. You feel like, okay, I know how this works. I know how these things go together. When you do an indirect proof, for me anyway, it makes you feel clever, because it's kind of, you're kind of thinking backwards, and this is a different kind of thinking, and I like it. It's my favorite kind of proof. So we need a couple of things here. First, we need to talk about how we say the opposite of something in math. So it's not saying the opposite of something in math is not always as easy as saying assume that it's not this thing. Sometimes it's a little more subtle. So let's look at some examples of starting an indirect proof. So for these first ones, the question is, what is the first step of an indirect proof? So for the first example, we're going to say we have a class of 30 students. And more students are right-handed. We want to prove that at least 16 are right-handed. I'm going to abbreviate it RH. So what we're trying to prove is that at least 16 are right-handed. And we're not going to actually do the proof. Well, we can talk about it. This is a pretty easy one. But we want to just say how we would start an indirect proof. So before we do that, though, let's think about a couple of other ways that we could say at least 16. So in terms of mathematically or with grammar, what's another way that we could say at least 16?
Less than some.
So it would have something to do with that. So we're saying that how many the number of right-handed students is, yeah? More than 15. Okay. We could say more than 15. So with what Alex was saying, we could say greater than 15. Greater than 15 students are right-handed. What's another way we could say at least 16? More than 16. Greater than or equal to 16. That would work. Greater than or equal to 16. And using words, what's another way we could say greater than or equal to 16? How could you translate greater than or equal to 16 into words? 16 or more. So all of these 4, 1, 2, 3, we came up with 5. All of these 5 ways are the same thing as saying at least 16. Prove that they're at least 16, prove that they're more than 15, greater than 15, greater than or equal to 16, 16 or more. All right, so to start a proof by contradiction, we're going to assume the opposite of this. Well, how do we say the opposite of at least 16? Less than, someone said it, less than 16. We could say they're less than 16, less than or equal to 15. That would work. But that our start of our proof by contradiction is we're going to assume that there are less than 16 right-handed students. Well, don't we get a contradiction right away? If there are less than 16 right-handed students, can more be right-handed in a class of 30? No. There can be less than 16 if more are right-handed. So already we've reached a contradiction. We'll talk more about contradictions in a second. So this would be our start. This is how we would start our proof by contradiction. Assume there are less than 16 right-handed students. And if you go further in math, one of the fun things about proof by contradiction or indirect proof is you get to use fancy language. So you could say something like, assume to reach a contradiction there are less than 16 right-handed students. Or assume, by way of contradiction, that there are less than 16 right-handed students. So you get to use some fancy language. All right, let's look at another one. So the second one. We want to prove that an integer, and an integer is, we could also think of it as a whole number, is divisible by 2. So that's what we want to prove. This one's a little easier than the last one. So we want to prove that it's this integer, this whole number is divisible by 2. To start a proof by contradiction, we want to assume the opposite. So what's going to be the opposite of that? This number is divisible by 2. What's the opposite of that? It's not divisible by 2. What's another way we could say a whole number is not divisible by 2? What kind of whole numbers are not divisible by 2? Prime, some, that would get some of them. Odd. Assume it's odd. Either one of those would work as a start of a proof by contradiction. Assume it's not divisible by 2, or assume it's odd. In this case, I would say, assuming that it's odd is probably going to be, just because I can see how you would do the proof, that's going to be an easier way to do the proof than assuming it's not divisible by 2. Assume it's odd. Sure.
Is this
So assume it's odd. So starting proof by contradiction, you assume the opposite. So this one you could say, assume by way of contradiction that the number is odd. All right, so the other thing that we need for a proof by contradiction is we need to know when we have a contradiction, when we've got something that is impossible. So let's look at picking out contradictions. So what I'm going to do for these examples, I'm going to say which two are contradictions. So I'm going to list 3 statements, and we want to know which 2 cannot be true at the same time. So the first set, I'm going to say a triangle is acute. The second statement is a triangle is scalene. And this means no right angles. And 3, a triangle is obtuse. All right, so let's look at these in pairs. Can an acute triangle have all different angles? Yeah? And not have a 90-degree angle? Yeah? So that's fine. Those 2 can both be true. How about 2 and 3? Can an obtuse triangle have all different angles? Yeah. Sure. And none of them are 90 degrees? Yeah, sure. No right angles. How about 1 and 3? Can a triangle be both acute and obtuse? No. Obtuse means that it has an angle bigger than 90 degrees, and an acute means all the angles are less than 90 degrees. So 1 and 3 are contradictions. Triangle can't be acute and obtuse. So if you were doing a proof, an indirect proof, and you started out knowing that the triangle is an acute triangle, and you did some work, and you came up with some information that said the triangle was obtuse, that would be your contradiction. B, second one. 2 lines are parallel. And we're going to say for the second one, 2 lines don't intersect. And for the third one, we're going to say 2 lines are skewed. And as a reminder, skew lines mean in 3 dimensions, like the downstairs main hall and the upstairs C wing hall. Like this. All right, so let's look at these in pairs. Can 2 lines be parallel and not intersect? Yeah, if 2 lines are parallel, they have to not intersect, right? And let's look at 2 and 3. Can 2 lines not intersect and be skew? If they're skew, they can't intersect. That's part of what skew means. How about 1 and 3? Can 2 lines be parallel and skew? No. We said skew lines did not intersect, but are not parallel. So 1 and 3 are contradictions because lines can't be skew and parallel. So that would be our contradiction. So if you started out with a proof, working on a proof, and you knew that the lines were parallel, and you did some work, and then you found out something that said that they were skew, you'd have a contradiction. All right, the last set. I'm going to draw a triangle here. And then I'm going to say this is a right triangle. So in triangle ABC, measure of angle A is 60 degrees. And in this same triangle, triangle ABC, measure of angle A equals the measure of angle C. And 3, in triangle ABC, measure of angle B is 90 degrees. All right, so let's look at this. We know this is a right triangle, and it says the measure of angle A is 60. The second statement says angle A and angle C are the same. So together, if both angle A and angle C are 60, what are they together? 120. But it's a right triangle. What would that make all the angles in the triangle? Thank you. 120 plus 90? 210. Is that possible? No, all the angles in a triangle are 180. Add up to 180. So 1 and 2. We know that angles in a triangle add to 180, not 210. Well, let's look at a couple of other pairs to make sure we're okay on the other pairs. How about 1 and 3? Could angle B be 90 degrees, angle A be 60 degrees? Does that work out okay? 90 and 60 is 150. So what does that leave for angle C? 30. That's okay, right? That's fine. How about 2 and 3? Can these two angles be the same and have that angle be 90 degrees? What would they have to be? A and C. Two angles that are the same and together they have to equal 90 degrees. They have to be 45. So we could have a 45, 45, 90 triangle. That would be fine. That's not a contradiction. So just 1 and 2 are contradictions. So if we were doing some kind of proof, and we knew that angle, in a right triangle, that one angle was 60, and then we figured out that another angle in there was 60, we'd have a contradiction. All right. So what I want to do is one quick example of an indirect proof, or proof by contradiction, the kind that you'll see in your homework. And this one's nice because it involves algebra, which is familiar to us. So we're going to be given that 5 times x plus y equals 50, and x does not equal 3. We want to prove that y does not equal 7. This is a really common place that you'll see in indirect proof when you want to prove that something is not true, because you can then start by assuming that it is true and show that that leads to some kind of problem. All right, so we want to do this with an indirect proof. So we're going to start by assuming the opposite of what we're trying to prove. Well, what's the opposite of y does not equal 7? Y does equal 7. Assume y equals 7. I think in our book they like to say assume temporarily. You can just say assume y equals 7. If you want to be fancy, you could say assume to reach a contradiction, y equals 7. Now we're going to plug in. If y equals 7, well, let's plug it in. We get 5 times x plus 7 equals 50, because we're given that. Well, let's figure out then what x has to be. Let's distribute. 5x plus 35 equals 50. Subtract 35. 5x equals 15. Divide by 5. And this tells us x equals 3. Is that a problem? Yes. We're given that x does not equal 3. So we would say, but x is not equal to 3, which is a contradiction. X cannot equal 3 and not equal 3 at the same time. This, assuming that x equals 7, leads us to a problem, leads us to a contradiction, leads us to something that cannot be true. So y does not equal 7. If y equals 7, x has to equal 3. And we're told that x doesn't equal 3. So y has to be something else. So that's how a proof by contradiction works. All right, questions? Okay. All right, there you go.